Okay, let's jump right in. You know, the biggest hurdle in making an eVTOL, like the P-13, a reality, it's not just about making it fly. It's all about the power. How do you safely wrangle and distribute over a megawatt of electricity through an aircraft that's going to be flying right over our cities? As a systems architect, that's the puzzle we live and breathe. It's a battle against pure physics, and it demands some serious, uncompromising engineering.
So what you're looking at here, this is way more than just a bunch of wires. This is the aircraft's nervous system, its vascular network. It's an 800-volt system, and every single piece of it, every connector, every harness, is part of a carefully orchestrated architecture. And believe me, the quality of this design isn't just about performance. It's literally what defines the safety of the entire aircraft.
You know, when you're facing a problem this massive, you can't just dive in. You have to be systematic. We take a top-down approach, breaking the whole thing down into manageable chunks. For the P-13's power system, that meant we had to win 3 crucial battles against the laws of physics. First, we had to figure out how to handle high-voltage electricity in the thin air at high altitudes. Second, we had to learn how to tame the insane violence of a DC electrical fault. And third, we had to shrink our power electronics to an almost impossible size.
Right, so our first battle takes us up to 25,000 feet. Now up there, the air, the very thing that's holding the plane aloft, suddenly becomes a huge threat to its electrical system. Trying to insulate 800 volts in what's practically a vacuum is a classic aerospace challenge, and it means you have to build your solution from the component level up.
So it sounds kind of backward, right? You'd think that thinner air with fewer molecules bouncing around would be a better insulator for electricity. But it's not. The answer is buried in some really fascinating physics that is absolutely everything in aerospace engineering.
And this is it, right here. This graph shows Paschen's law, and it perfectly lays out our problem. As the air pressure drops, when you go higher, its ability to stop electricity from jumping across a gap, what we call its dielectric strength, just plummets. So a system that's perfectly happy at 800 volts on the ground is suddenly in a super high-risk zone for something called partial discharge, or PD. You can think of PD as tiny, corrosive lightning strikes that just eat away at your insulation until eventually you have a catastrophic failure.
The engineering principle here is actually pretty straightforward. If you can't trust the environment, well, you have to build your own. We basically decided we couldn't rely on the thin air for insulation at all, so the whole system is designed to be totally self-contained. We use components like these connectors that are literally certified to be partial discharge free all the way up to 50,000 feet. We pair that with advanced wiring that has its own bulletproof insulation, creating a completely sealed and controlled electrical world inside the aircraft.
Okay, on to battle number 2, and this one's all about brute force. What in the world happens when a megawatt-class DC electrical system has a dead short circuit? I'm not talking about a little spark. I mean a literal explosion of energy. Containing that violence is one of the most critical safety jobs on the entire aircraft.
Just look at this. On the left, that's the raw, destructive power of an uncontrolled DC arc. See, unlike the AC power in your house that flickers on and off, a high-powered DC arc doesn't stop itself. It just keeps burning with the intensity of a plasma cutting torch. Our job, our entire goal, is to get what you see on the right, an intelligent, instantaneous containment that snuffs out that fault in just thousandths of a second.
So how do we do it? We use a philosophy called defense in depth. It's all about layers. First, in less than 10 microseconds, that's millionths of a second, a solid-state power controller electronically trips to shield the sensitive stuff. But if that's not enough, then in under 1 millisecond, a pyrotechnic fuse fires. Think of it like a circuit breaker with a tiny explosive charge. It's the system's airbag, and it physically blows the connection apart. Finally, about 15 milliseconds later, the big mechanical contactors open up for complete physical isolation. Each layer is just a faster, more aggressive backstop for the last one.
And all of this is happening on top of passive safety systems that are on guard 24/7. First, you've got the high-voltage interlock loop, or HVIL. It's a simple, low-voltage wire that snakes through all the big power connectors. If any connector even starts to come loose, that little wire breaks first and screams at the system to cut the power instantly. Then there's the insulation monitoring device, or IMD. It's like a smoke detector for the electrical system, constantly sniffing for any signs of trouble. And finally, active discharge circuitry makes absolutely sure the system is safe to touch within 5 seconds of shutting everything down. All right, our third and final challenge, and honestly, this is the one that really defines all of modern aerospace engineering, the never-ending war against weight. Every single gram matters. So the question is,
How do you make your power electronics smaller and lighter while at the same time making them way more powerful and efficient?
I mean, the pictures here really tell the whole story, don't they? On the left, you've got a traditional power converter, big, bulky, heavy. On the right, a modern unit built with these incredible new materials like silicon carbide. The reduction in size and weight is just staggering. And in aviation, weight is everything. Every kilogram you can shave off the power system is another kilogram of cargo you can carry or another few kilometers of range you can fly.
And the result of all that new tech is this number, a power density of over 2.5 kilowatts per kilogram. Now, to put that into perspective, that's more than 3 times what we considered state-of-the-art just a couple of years ago. This isn't just a small step forward, it's a giant leap in performance. It's the kind of breakthrough that actually makes an aircraft like the P-13 a viable business.
And one of the secret weapons that lets us hit that density and reliability is a component that has a genuine superpower, self-healing capacitors. See, in older designs, one tiny internal short in a capacitor could cause it to fail, which could take down the whole power converter. But these new ones? If a microscopic fault happens, the material right around the fault instantly vaporizes, isolating it and basically healing itself. It's an incredible innovation that massively boosts a system's long-term reliability.
So, okay, we've designed a system to beat these huge physical challenges. But in aerospace, designing it, that's maybe half the battle. Proving it is safe, that's everything. And this is where we have to run the gauntlet of verification and testing, trying to prove our system is safe to an almost unimaginable standard.
1 in a billion. Just let that number sink in for a second. That isn't a suggestion or a target we hope to hit. That is the law that we have to design to. The entire electrical system, from every single line of code to every bolt, has to be proven to be so incredibly robust that a catastrophic failure is statistically expected to happen less than once in a billion hours of flying.
And the way we prove it is by following what's called the V model. We start at the bottom, testing every tiny component in isolation. Then we build them into bigger pieces and test again. And finally, everything comes together on this rig, our Copper Bird. It's basically a full-scale replica, an electrical clone of the aircraft's entire power system built on the ground specifically so we can torture test it in ways you could never, ever risk on an actual flying plane.
And when I say torture, I mean it. We stick components in vacuum chambers to simulate high altitude, hunting for any hint of partial discharge. We bolt them to shaker tables that pound them with years' worth of vibration in just a few hours. We cook them and freeze them, cycling from Arctic cold to desert heat over and over. And on the Copper Bird, we do the unthinkable. We intentionally create the worst possible short circuits to prove, beyond a shadow of a doubt, that our layered protection system works in milliseconds every single time.
You know, this table really gets to the heart of certified aerospace design. It's all about traceability. Every single engineering decision we make, from choosing those PD-free connectors to using a pyro fuse, is directly and explicitly tied back to a specific rule in an international safety standard. There is absolutely no guesswork. It's a completely closed-loop system of requirements, design, testing, and proof. So when you put it all together, the high-altitude design, the millisecond fault protection, that insane power density, and the brutal testing to prove it all, you don't just get a collection of parts, you get the lifeline. You get the critical enabling system that finally makes safe, quiet, and efficient urban air travel a real possibility. The level of engineering we've just walked through really does set a completely new benchmark for safety and performance in electric aviation. This isn't just a small evolution, it's a foundational change. So the real question it leaves us with is, now that we know this level of safety is possible, what new doors is it going to unlock for the entire future of flight?